Yeah, thank you. Yeah, indeed, it's very nice to see so many of you, especially after the competition from yesterday. So I would say that's the usually that's where I lose most of people. But yeah, and also prove is a strong word. I think I should just put that for the record because some of my friends, math friends, might be upset. Okay, so let's go back to where we were yesterday. So let me just give you a brief recap where what we were trying to do. So we are trying to derive a high-dimensional asymptotics for this problem that I introduced called the generalized linear estimation problem. So this is the problem where the statistician observes some data. So you can see it's like kind of a supervised learning setting where data come in pairs of labels and covariates. So covariates, I'm going to assume, is in Euclidean space RD, and labels can be like in a set, which can be discrete potentially. So if you want to think about classification, for example. I'm going to be assuming that the data generating process is the following. So yi only depends on xi through a likelihood on the projection of xi in a given direction. So in the end, the problem really is the problem of estimating this d-dimensional vector theta star. So theta star comes from a prior distribution. So you can think this as a constraint on theta star. Let's say theta star is k-sparse, or theta star has norm 1, or theta star like satisfies some properties. So you can think this is like this distribution is parameterizing this constraint on the signal. And that's perhaps like our strongest assumptions are going to assume that the covariates are Gaussian IID with a covariance sigma. But okay, the motivation for why this might be a good idea, I leave to Cynthia's lecture, so she already motivated and give a good motivation. So I hope that everybody is convinced that that's a good setting to study in high dimensions. Then the problem is that we want to learn or infer theta star from the data. And here we introduce, let's say, different methods where you can approach this problem. One of them was this kind of Bayesian inference setting where we might have some information about the data generating process, and then we are just going to build a posterior distribution for theta given the data. And this posterior distribution could or not use the full information about the data generative process. So if you use the full information about P star and P of theta, meaning that psi equals to P star and phi equals to P of theta, that's what we call Bayes optimal inference. And then the posterior gives essentially the best type of estimators you can hope for in this problem. However, you could also think about doing Bayesian inference in a setting where you have just limited information. So I was just giving an example before we started. Like, let's say that your signal is k-sparse, but then you know it's sparse, but you don't know the level of sparsity. So you might put a prior which is k prime sparse, and then you want to see what happens when you don't have this, like, when you have this mismatch between your posterior and the true posterior. You could also think about these guys being not probability distributions, but being kind of some pseudo distributions. And this allows us to treat the case of empirical risk minimization. So the point of studying this thing is just that you can put several things in the same umbrella. And this highlights a bit the universality of this type of methods. Like you can treat several problems in the same way. Finally, we were working under these assumptions that the dimensions diverge at a fixed ratio. So that's what we call the high dimensional regime or the proportional high dimensional regime, because n is proportional to d and the proportionality constant is alpha. Sometimes we call this the sample complexity. And since we are working in a asymptotic regime, we need to make sure that we that the quantities which are d-dimensional have some meaningful scaling. So here we're going to assume that the norm is order d and the trace of the covariance is order d. And the approach to try to study this problem that I was introducing yesterday is the replica method. And it follows 6 steps. And so we went over step 1, 2, 3, and 4, and we left in the beginning of step 5. So the step number 1 is the replica trick, where you just expand the logarithm of the partition function in terms of powers. So you can write the expected free energy density as a function of the moments of the partition function. Then you take the average over the disorder or over the data. So here the data plays this role of disorder. And then finally, you massage the expressions in order to make a energy and entropy decomposition of whatever is left after you take the average. And then once you write this, you find yourself with some horrible integrals, the exponential of d times the potential. And this potential is going to be our large deviation potential, like large deviation rate. And now we take the d going to infinity limit and use the saddle point method to write this integral as the extremum over the potential that you achieved. And that's where we left last time. Of course, like the thing left is to take the limit of the replica going to 0, so s going to 0. Actually, the derivative of this extremization problem, and then take to 0. So that's where we left last time. We derived this expression. So this is just the expressions that we derived last time. And I guess that we went like really, really slow up to here. So today I'm gonna accelerate a little bit because since it's the last lecture and I want to give you some idea of why this is useful. So let me go a little bit carefully over this step, and then the last step I'm gonna go a little bit faster. So now, if you think a little bit about this problem, what we achieved here, yeah, sure. Oh, sorry, that was a typo then. Yeah, it's a norm squared that is ordered. Yeah, because so really this is scaling. What we want behind it is the fact that these scalar products are order 1. Because you see, the objects that appear in the extremization problem, they are the moments of these pre-activations, if you want, in machine learning language. So in physics, we call this the local fields. And so the moments of the local fields, so the joint moments of these two local fields, give us these order parameters, summary statistics, overlaps, whatever you want to call it. So we want them to be order 1 in the limit, because when we take the limit, we want this potential to be order 1 such that we can apply the Laplace method. So that's like, reverse engineering why we need these assumptions, and why I'm stating then, even though, as I said, I'm not being precise on a mathematical level on all the assumptions you would need to get the result, because anyway, the method is heuristic. But I think this is a, like, let's say, meaningful assumptions at this point. While if I would assume, let's say, the likelihood or the prior is kind of a bounded support, or this likelihood is a Lipschitz function, it would be meaningless at this point, given the level of rigor of the method. Although these are assumptions that you need to prove the formulas in specific cases that you can derive. Okay, so in the end, you can see this extremization problem, just like for the Curry-Weiss model, you're extremizing over something which is a sum of an energy term and of an entropy term. The entropy term counting how many configurations there are with fixed overlaps, and the energy term counting the energy of each configuration. So this is just like in the Curry-Weiss model, just that this Curry-Weiss model was much, much, much simpler to write this decomposition. And now we have this horrible expression. Now, if you think a little bit about this problem, you realize that we didn't achieve much, because solving the extremization problem is extremely hard, because essentially is an optimization problem over space of the matrices, which are S by S, vectors of dimension S, and then these two scalar variables. So how do you even go around solving this thing for these things? Like, you cannot even put in the computer. And after, even if you could for a fixed S, then you have to take the limit S going to 0. So yeah, just think a little bit how you would approach this with a Python like Jupyter notebook. So the idea now is that we need to use some simplification of that. And the simplification of that is like making some ansatz for how the solution of this problem should look like. And here is where it comes, I tried to motivate last time, like the genius of Giorgio Parisi. Because essentially, the large deviation principle tells you something about the measure, right, in high dimensions. And so guessing how the minimizer of this problem should look like is telling you something about the geometry of the measure in high dimensions. And so it's not obvious at all what are good solutions, like just looking here. And what Giorgio did is that he came up with a recipe to essentially build a hierarchy of different ansatz and to check whether they are correct or not in a principled way, let's say. You make an ansatz, you check if it is the good solution. If it is not a good solution, you move on in the hierarchy, and then until you find the solution. And eventually you find the solution if you follow like enough steps. So here we are going to see the simplest ansatz. And the reason is that the simplest ansatz is already satisfying for many problems that we are interested, not for all. And of course, like if you are interested in this thing, the idea is that this is just like, a taster to get you interested in the topic, and then you can go and dig, and if you need references, let me know. So what is the assumption is what is called the replica symmetry. So you assume that we have for all A, MA is equals to M. So M is homogeneous. So remember what is M? M is that I draw a sample from this distribution and I compute the correlation with the target. And this is the correlation with the target. So I'm going to say that, whatever in the high dimensional limit, whatever sample that I take from the Boltzmann-Gibbs distribution will have a fixed correlation with the target. So this is not varying. It's going to concentrate. And then we're going to assume that QAB equals to R for A equals to B. So there's a diagonal element, and there is an off-diagonal element. Meaning that if I took two independent samples from the posterior and I compute their correlation, they always have the same correlation in the high dimensional limit. Again, this is like a concentration assumption on the overlaps. And then it's easy to check that, if you make these assumptions, you should also make these assumptions on the conjugate fields or the conjugate overlaps. And since we are extremizing over them, I'm also going to make, just for convenience, I'm going to dump some constants here. So I'm going to just assume that's -1/2 of R hat, because the expressions look nice if I put this 1/2. But of course, it's without laws of generality because I'm extremizing over these things. Right. And that's for OA. Okay, that's the simplest level of what do we call like the replica symmetry breaking scheme. So the step 0, which is when the measure is replica symmetric. So just let me make a comment, so a remark that can be proven to be exact, meaning that replica symmetry holds in two scenarios. So the first one is Bayes optimal inference. And let me remind what I mean by that is that when you have this setting, so you can prove that the resulting formula that you're going to arrive very soon, it's exact for this problem when you have Bayes optimal inference. And the second case is convex ERM. So that's the case where your likelihood y given z is equals to minus beta, a loss function that you choose, and phi of theta is equals to the regularization parameter. So if you choose a loss function which is convex and a regularization which is convex, you can prove the replica symmetry it's exact. And that's kind of not so hard to see because the resulting measure is going to be some kind of log concave measure, so it's going to be easy to show that. And by the way, let's just make things even more concrete. Like that's the case for ridge regression. That's the case for the lasso. That's the case for logistic regression. That's the case for yeah, many other like settings that you can think about, like Uber, like robust regression, so on. Okay, and now that we have these assumptions, like it becomes clear that it's kind of easy to take the limit, right? Like let's take a look at like the simplest term. So these terms here. So for example, sum over MA, since all the A's are equal, this is just S times MA. So the derivative is just MM, and then you can take the limit, right? So replica symmetry allows us to simplify. So for example, A MA M hat A equals to S times M hat. So easy. And then you can also simplify the entropy and the energy potential. This is slightly more complicated. Let me do one explicit example for you. So just to get the flavor, because there is a little bit of there's a little bit like of a little trick that we use that is very useful in this computation. So let me just give you how it works for this one. So let's go. Oh, that's 5 psi. Not this phi, this phi. Okay, so what is this? This was 1 over d log. Let me just, as a shorthand, write expectation over theta star for the integral over theta star. And then what you had is something like integral a d theta a phi theta a. And then we had this exponential. And then if I apply the replica symmetric assumption, you can see that this is going to be something like rho hat theta star sigma theta star minus r hat plus q hat over 2 sum over a theta star sigma theta a. And then there is a third term that is actually the annoying term, which is q hat over 2 sum ab theta a sigma theta b and close exponential. Okay, so what I did is that I just took this expression here and I apply replica symmetry and I simplify this sum, right? And you can check that this sum can just be rewritten in this way. And now you can see that almost all terms are good. Like, so this term is proportional to sum of A, so it factorizes in A. The measure is factorizing A because the prior is factorizing A. So this allows me, I want to write this as like, a product over A with the whole thing, but then I still have this term that couples A and B, and this is the annoying term. So I need to decouple this A and B. So what do you do is that always in physics, when you have like a quadratic coupling between two variables and you want to decouple them, you use what is called the Hubbard-Stratonovich transformation. So Hubbard, and that's why I wanted to go over detail in this, because this is a useful trick. Stratonovich. Which is a trivial identity in maths, but it's so useful that in physics we give it a name, which is to write exponential over q hat over 2 sum ab of theta a sigma theta b. We're going to write this as exponential over square root of q hat sum over a psi theta a, where I introduce this psi. Psi is just going to be a Gaussian vector, where psi So essentially, you can see that by introducing this Gaussian vector, if I take the expectation over this quadratic form over the Gaussian vector, you just get like the quadratic coupling. Okay, this is just like Gaussian integration. But this is very useful because now I have a sum over A and not a sum over A and B. Of course, I introduced something new, but it's just one Gaussian vector. Doesn't depend on, doesn't have an index A. That's the key step. Okay. So with that, we can rewrite phi theta of S as the 1 over D log of expected value over theta star, expected value over this new Hubbard-Stratonovich variable of something which is decouples in the replicate space. Actually, yep. Because when you integrate over xi, you get the sum squared. Yeah, it's just Gaussian integration. but it's a nice trick that. Wait, I have to put something outside here. I have to put E of rho hat. Rho hat theta star sigma theta star, and then I can open my bracket. Theta I of theta exponential of m hat theta star sigma theta minus q hat plus r hat over 2 times theta sigma theta, and then plus square root of q hat sigma. No, cannot do that. Sigma needs to be in the quadratic form of psi sigma 1/2 theta. Okay, and then I have everything to the power s, because now everything is just decoupled in s. Everything is like sum over a, so I can just factorize. And then now it's easy to take the limit, right? I just have like the limit of log of expectation of something to the power s, and I can take the limit. It's easy. Okay. Okay, so I claim, and that's gonna be, you have to believe me, is I claim that you can repeat the same thing for the energetic potential to be able to decouple whatever interaction between the replicas you're gonna have here. You can apply the same thing, and essentially the main step is gonna be to use Hubbard-Stratonovich again, okay? But now we are gonna do a little jump. So the step 6 is that once you apply replica symmetry to everything, you take the limit. And I claim that once you do that, it's easy to take the limit. And then the conclusion is that the free energy density is going to be written as an extremum. And I'm going to just have 6 variables. So m hat, q hat, r hat of minus m hat plus 1/2 r hat, or yeah, minus 1/2 q hat. And then I have these 2 potentials that have been simplified now. So I drop the index s. This is a function only of m, q, and r, and plus the potential, the entropy potential, which is only a function of m hat, q hat, and r hat. And let me give you the expression for these things. So this guy is the expectation. Then here there is another Hubbard-Stratonovich that I need to introduce. there is the dy. There is one function that looks like this. So this is the first one. I'm going to define what this z is. Just bear with me a second. And this one is going to be the expectation. So there's going to be, sorry, I need to write it properly. So limit as d goes to infinity of 1 over d of the expected value. So there is expected value over the prior, over the Hilbert-Sutton of each field. And then I just have the log of d theta, phi of theta, and this exponential that I already wrote before. Here there is theta sigma theta plus m hat theta star plus q hat sigma 1/2. Oh, you can put this in the square root. Psi transpose theta. And finally, I just need to give you what this function is. So this function star is just the expected value over a Gaussian random variable. Actually, it's one-dimensional Gaussian variable of p star y given v1/2 z plus omega. And the equivalent one for y is the expected value over z. You can probably guess at this point of psi. Okay, so that's the expression. Done. That's the high dimensional asymptotics of the problem. It looks ugly, but you cannot have hoped for much better. We are treating a huge class of problems under one expression, right? I claim that if you tell me what is your favorite problem, compressive sensing, for example, so you have a Gaussian likelihood and a sparse prior. All these things simplify enormously. So let me make just one comment about the interpretation of this thing. So you can notice that these guys, for example, they look like the convolution of the likelihood with a Gaussian variable. So essentially, one way of interpreting this thing is that the high dimensional problem is effectively equivalent to a low dimensional problem where you just now have to denoise some variables. So here is the denoising of some z, that y, which is equals to some z, which has some variance and some mean. And here is the denoising of a vector, which has been noised, and the variance and the mean of the vector depends on these overlaps. Okay, so I could write down the effective denoising problem, and then if you write down the large deviation principle for this effective denoising problem, or if you write down like the free energy for this problem, it would be equals to the free energy of the original high dimensional problem. Okay, so I'm not going to go into detail on that, but it's just to give you a little bit of an interpretation. Questions about the expression? Because now, otherwise, we're going to go and see something a little bit. What can you do with that? So just before, let me make a remark, because as you notice, I've not been giving a lot of references. So the replica method and the Curry-Weiss model and all of these things are quite standard things in physics. They have been known for a very long time. And I think we can treat at this point as kind of a common knowledge in physics. Now, the application of that for generalized linear estimation is something much more recent. So let me give you a little bit of a pointer. Of course, the main credit that I should give is for Giorgio Parisi to finding this type of ansatz for the replica method. So remark one is that for base optimal So for base optimal inference, this formula can be proven. Let me call this star. So this large deviation principle star can be proven using something called Guerra's interpolation. So Guerra was a mathematician working in Rome. Like sadly, he passed away, I think, 1 week ago. So very sad. Like, so he was a mathematician working in Rome, and he was one of the first ones to prove some version of Paris's result. So the method that he developed is called interpolation, and you can use interpolation to prove this formula when you are in the base optimal setting. And this is something that was done in a paper of some colleagues, so Jean Barbier and a bunch of other friends, like in 2019. So Lenkas Deborova, Florent Jacala, Nicolas Macri, and Léo Miolan. So they proved this formula in 2019 using Guerra's interpolation. So for convex ERM, so what is interesting is, as I told you, I think 2 lectures ago, or maybe 1 lecture ago, is that this formula, the result of the replica method, so the replica method cannot be proven, but the result of the replica method can be proven in specific cases. And interestingly, it requires different techniques in high dimensional probability for each of these different cases. So for convex ERM, this can be proven using something called CGMT. So that's convex Gaussian mini. What is again? Oh, I forgot. Minimax theorem. So this has been done by Trampolidis et al. Um, 18. So a lot of works also of Stojnik. So and there is also some work by myself that essentially prove this formula for convex ERM under this generic setting that I'm presenting to you. So when you have a generic convex regularization, generic convex loss, and a covariance matrix. Because I think the first works by Christos were for specific cases, like, for example, compressive sensing, logistic regression, and so on. This can also be proven using AMP. And here we have like works by Cincha. We have works by Montanari and his group. So I'm not giving specific, like if you want specific pointers, check in the notes. I try to cite most of the original papers that prove this in specific settings. And there is also work by Cédric Gerbelot that is proving this formula under different like convex ERM settings. Okay, so now it comes, I think, yeah.
So when you say that this cannot be proved as is and it has to be proved in each instantiation,
yeah.
Do you mean, so the only thing that is non-rigorous, that possibly cannot be made rigorous, is the assumption, the answers? Is that the step that you are?
So even the answers, I think, is kosher. Like I think that because you're just making an assumption on Q, but then like taking the analytic continuation from S being an integer to being a real number that you can actually take the limit, this is a problem. And this is related to the answers, of course. So this is a big problem. I mean, okay, I'm putting this as like kind of an open mathematical problem, but I don't recommend you to work on that. So like, there are loads of people that have been there since the 80s, and yeah, has not looked very good, like the progress that was made in trying to provide a general rigorous argument for replicas. However, what the situation at the moment in this community is that, for some time, and maybe Cynthia can also comment on that, is that for some time, essentially only physicists knew how to derive results for some of these problems. And mathematicians didn't have like the tools to derive from scratch the results for these problems. So they could see the formula, they could use interpolation or something to prove the formula, but they were not able to derive from scratch. Now the situation now is that there are as many rigorous tools to derive results for specific like instances of that as the replica method. So nowadays, like the standards in the field is that, most of the times you need to have a proof. And so people mostly use AMP for that because AMP is very flexible. It's one of the most flexible tools for proving. So interpolation is very suited for the base optimal case. It completely breaks down the argument when you are not base optimal. CGMT is very good for when the problem is convex, but when the problem is not convex, you don't know what to do. You just know how to derive bounds. AMP is the kind of the tool that is resilient to both like non-base optimal inference and non-convex ERM. However, I'm not saying that it's easy to cook up these proofs. And I mean, you can see Cynthia's papers like, 80 pages at least, like for doing that for one problem. So, it's pulling out these proofs is hard. It's like, it's work.
So the only issue is this non-integrality of this. At least in this argument. But
yeah.
These proofs don't take this approach. They take a completely different.
They take a completely different approach. Yeah.
To overcome this.
Yeah.
Because you can't.
Yeah, and if you look at the most AMP papers, they were going to start consider this sequence of iterations. We prove there is a state evolution, and the state evolution, that's actually my comment next. So I'm not going to spoil, but there's a state evolution, and then you need to control the iterations of the state evolution and prove that the trajectories converge, and the minimizer, like the trajectory converges to the minimizer of this problem. Something like that. And then usually the very hard part is like actually controlling these iterations, because the state evolution proofs now are kind of well understood. So controlling the iterations is one of the, yeah. Great, yeah. Well, feel free to make any comment, because now now we are getting like towards the same thing. So that's the moment we can start to interact. Yeah.
So the data point set.
Yeah. So concentration of what? So yeah, it's that the integral is gonna concentrate on the extremum of the potential. Yeah. So it's just a standard like Laplace method, but if you want to do it properly, you need to do it in the complex plane.
Okay, but why do you call it saddle point then?
Oh, it's just because. So yeah, Laplace method in the complex plane sometimes is called saddle point method. Yeah, you can also call Laplace method. I like it more because, Laplace.
Like a variation.
Yeah, exactly. Yeah, there's nothing more to it. Like it's nothing.
Then another quick.
Yeah.
That's basically just the characteristic function of the Gaussian.
Yeah. Yeah.
Okay.
Yeah. Also, it's like Stein's lemma, right? Like whenever a mathematician says, "Oh, it's Stein's lemma," the physicist is like, "Integration by parts? Like, why do you call it Stein's lemma?" And then whenever we say Hubbard-Strotunovich transformation, the mathematicians are like, "What? It's just Gaussian integration." So, it's this kind of thing. Yeah. Right. Yeah. Right. Okay. So as I said, like our approach here has been to reduce this variational problem over matrices to something over scalars, which allow us to take the limit. Now, what happens is that this is just like, an answer. So it might not be the true minima, the true extremizer might not be the one that we found by solving these equations. So how do you check whenever you do an ansatz of an extremization problem. You check the stability. So you move a little bit away from the solution, and you see if you can find something that has lowest or higher energy because you're extremizing around the ansatz. That's exactly what you do. And if it is stable, means that it's good, then you stop. If it is unstable, then what you should do is that you should consider some other family which is richer. So it's a hierarchy like. So replica symmetry is a particular example of replica symmetry breaking. So replica symmetry breaking is going to start to add some structure to this matrix. So you have this matrix QAB. I said that is a diagonal plus off diagonal. Now you could consider like some block structure. And which block structure, Paris is going to tell you what block structure to choose. And then you do one replica symmetry breaking. Does it work? Oh, yes, maybe no. You check the stability, doesn't work. And maybe you have to go two-step replica symmetry breaking, 3, 4, 5. And then full replica symmetry breaking actually would mean that you would consider this matrix become a function of A and B. And then you would have a variational problem on this function. And actually this function can be written as a probability measure over something, and then you can well define this variational principle, and this is what is called the Parisi formula. But this is problem specific. You have to give me one loss function and one regularization or one base inference problem. And for that problem, I can tell you what is the level of replica symmetry breaking. It's not easy, but we know for a couple of problems what is the level. For other ones, we don't know, and you have to actually do the stability analysis. Okay, let me see how I'm doing on time. Yeah, okay, I guess I need to move fast because I want to tell you guys some cool stuff. Okay, so essentially we are done at this point with the replica method. And I just want to tell you one very, very important fact, which is essentially the culmination of all the lectures, if you want. Like, so you have to learn one thing here, you learn that. So a very important fact. Is that extremizing star. So what I mean by that is that, remember the Curry-Weiss model, we got the variational principle for the large deviation potential, and what we did, we take the derivative, we extremized, and we try to find some equation, which we call the mean field equations or self-consistent equations, that solutions of this equation extremize that. So extremizing these meaning like, take the gradient, set to 0, and then this is gonna give you some equations. So let me do it very abstractly here. So I don't want that. Is going to be some function m hat q hat. So I claim that if you take the derivative, you can essentially find a nonlinear self-consistent equation, just like we did before, and that's easy to see because you extremize respect to m, then you get m hat equals to derivative of this guy, right? So you can just write down this thing. So the extremizers of this potential are exactly the state evolution equations for AMP. Okay? So Cynthia is going to derive these state evolution equations. What they are tracking the performance of AMP as you iterate AMP. Okay? And the equations will take the form where you put some time indices and you iterate t plus 1. Is equals to some function of the previous iteration. The claim is this equation is equals to Cynthia's equation, okay? It's crazy. It's mind-blowing because there's nothing that I did here that has any relation to any algorithm, okay? I'm just trying to characterize the large deviation principle of a Bayesian inference problem of like some Boltzmann-Gibbs distribution. It turns out that the extremum of this large deviation potential satisfies some equation, which is the state evolution of some AMP. As long as you initialize them at the same point, they will have the same trajectory. Okay. Questions about this, because this is very like this, you know, that's the climax.
You're saying that the solution of the problem can be written as a 6-point equation.
Yeah.
And then to solve a 6-point equation, you are using something like a Banach equation.
Yeah.
Repeatedly.
Yeah. Yeah. Exactly. Yeah.
That's essentially what AMP is.
AMP is exactly doing. So the performance of AMP can be tracked by some equations, and these equations are exactly extremizing this potential. As long as you iterate with this time ordering that you're saying.
So this F, does it have some properties? If I think of Banach's point theorem,
yeah,
it says that you'll have convergence only when the operator is a conjunction.
Exactly.
So do you have such properties?
So yes, that's a good question. When the problem is convex ERM, typically that's the way you prove convergence of AMP, because this thing is contractive. Now, in Bayes optimal inference, as we're going to see, this might not be this potential might not be convex. So, you know, even if you contract, you might contract to the wrong place, like, right? Like you might not minimize, you might not actually extremize. And that's when AMP is going to get stuck as well. And we're going to see this now, but yeah. Yeah, exactly. Yeah, that's also a good question. So these are conjugate. So remember where they came from. They came from when we were computing the entropy, we were imposing the constraint that the overlap should be, because, you know, we started with introducing this M, but this was just like a name, right? A variable to call the correlation function. But then we wanted to separate entropy and energy, and the way to do that is that we need to, in some sense, free we need these parameters to actually be dynamical variables. So we introduce a constraint, Laplace multiplier, that actually separate the definition of M from from M, right? So that you have like in one side something that imposes the constraint, and then M is a free variable now that we are integrating over. So it turns out that if you like essentially extremizing over the hats are imposing the constraints that this thing should be the correlation functions.
You're saying the hats are like dual variables?
Yeah.
I thought they were like Fourier transform.
So they come as imposing, so they had the delta function was like Q equals to something like theta A sigma theta B. Then I went to Fourier space and essentially I got these hats. Yeah. And these hats, they are, you know, if you extremize over them, essentially is like integrating over the variable, which is essentially fixing the constraint, right? That's what I mean. Maybe not dual, like in the sense of duality, yeah. But
so actually, now that we're talking about this Fourier, I have a related question.
Yeah.
Weird question.
Yeah.
So this uncertainty principle, Heisenberg uncertainty,
yeah,
which is just a fact about Fourier transform.
Yeah.
If you take the primal and dual variables, there is this uncertainty. Is there something like that with these, or is it complicated?
So, not that I know. I don't know. Yeah, maybe the short answer is I don't know. Since we don't have a lot of time, maybe we can chat about this later. Okay, so that's a very deep fact, and you know took a lot of time for people to realize that. And but is that actually this large deviation principle is related to an algorithm. It's astonishing. And by the way, you need to choose the right AMP, right? That's the AMP that has the denoising functions or the denoisers that correspond to this thing. So if I write explicitly, just to connect to what Cynthia is going to say. So if I need to choose these denoising functions of AMP that is going to appear in the AMP. This needs to be the derivative of log of zy, and this guy needs to be the derivative respect to b of log of zb of z. So that's y. This is this guy, and this is going to be, there's an equivalent to it, which is essentially this thing that I'm integrating over here. So I call this zb log of zb. The derivative of that should be the denoising of the AMP that you say later. So a very important consequence of this very important fact I mean, I like the music. It's like it's inspiring. Like, you know, it's like we reached the climax, and now it's just like joy and party because it's perfect. Thank you for arranging that, Steve. Yeah. So so when we are doing base optimal when we are doing base optimal inference, so again, let me remind you what this means. When we have the right likelihood and we have the right prior, so that's what I call base optimal inference. So actually my measure is the posterior measure of the data distribution. So these guys, these denoising functions of AMP, they are the optimal denoisers. Because remember that these guys depend on the choice of P star and sorry, psi and phi. So these are the optimal denoisers. And what this implies is that AMP is actually extremizing extremizing the base optimal posterior free energy. So that's crazy, right? Like, I mean, if you have the optimal like Bayesian posterior, then you have an algorithm that the iterations of this algorithm is trying to sample from the optimal like posterior, which means that this algorithm is somehow optimal, right? Because if the posterior is the optimal posterior, trying to sample from it is the optimal thing to do. So I'm not saying that the algorithm is always going to manage to obtain a sample from the posterior, because the posterior might be complicated, but at least you can see the iterations of this algorithm as minimizing this phi. And when this phi is simple, you're actually going to achieve it. So you're actually going to be able to sample from the posterior. And when this phi is complicated, maybe you fail. And that's the, I guess, the last thing that they're going to discuss today. Let's look at an example, because for now all these things is a bit abstract. But now I want to connect back to the question of hardness in learning, because this is the source of the conjecture that AMP is optimal, right? Like, it's the fact that AMP is actually, when you choose the denoisers to be the optimal denoisers, is actually trying to do the optimal thing statistically. Right. So, by the way, okay, that's just put this as a comment. This leads to a conjecture of AMP optimality. And this conjecture that Cynthia mentioned yesterday, actually, so optimality among polynomial algorithms. But we know this conjecture is actually false, but as every good conjecture, you know, it's false in some cases, it's true in some other cases. These are all the good conjectures. So it can be proven something is slightly weaker, and this is approved by Celentano and Montanari, I think 2021, that prove that this conjecture is true among first order methods for this class of problems that we are looking at. So for first order algorithms, AMP indeed is the optimal algorithm. among all polytime algorithms, we know is not true, but we know is like morally true. I'm gonna explain this. Okay, we believe it is morally true. That maybe is a better way of putting. So let's look at a case study. And that everything that I'm saying is going to become a bit more concrete, which is going to be the phase retrieval problem. So everyone has its favorite problem. That's my favorite problem in this class. So the phase retrieval problem is the problem of you observe y, which is the absolute value of some theta star xi plus some Gaussian i's, and your goal is to recover back theta star. And so if you translate this to our language, that means that the likelihood P star given Z is, so that's the noiseless phase retrieval. So that's the likelihood that we should take. I'm going to take the prior to be very simple. So I'm going to take theta star to be just Gaussian. What happens with sparsity is interesting, but, oh, sorry, no noise. Otherwise, this would be a Gaussian. So P of theta is the Gaussian distribution. And I'm going to be assuming that we are base optimal. So this is also equals to psi of y and z, and that's equals to phi of theta. Okay? So really, really, really simple setting. So remember that in lecture 2, or I don't remember if 2 or 3, or I stated something called the Nishimori identity. Nishimori identity. That tells you that under the base optimal setting, samples from the posterior, like expectation of functions of samples of the posterior, are equal to expectation of samples from the posterior and the prior. So this implies that Q equals to M, that M hat equals to Q hat equals to R hat, and that's it. And R is equals, and this is equals also to, sorry, not this. R is equals to, now let me remind, so V equals to, so R equals to 1, and R hat is equals to 0. Okay, so this is something that can be checked from the Nishimori identities. Let me go a bit fast over here, so otherwise we're not gonna get where I want. But if you have questions, ask me. And then this means that my six variables now are reduced to 2 variables. And I just need to solve like a 2-dimensional extremization problem. So believe me, the self-consistent equations, they look like that. So Q of time t plus 1 is going to be Q at time t, Q hat at time t, 1 plus Q hat at time t. And then Q hat at time t is equals to alpha 1 minus Q at time t squared, expectation value of eta, and psi of 1 minus eta, sorry, 1 minus Q eta plus psi squared then H Q 1 minus Q psi eta plus Q 1 minus Q psi squared, everything squared, minus Q of t. Close brackets. And then here psi and eta are just 2 effective Gaussian variables. Like, oh, by the way, sorry, I forgot to mention that I'm also taking the covariance matrix to be identity. So this extremization problem essentially boils down to find the fixed points of these equations. And you have 2 equations now because the Nishimori identity reduced my problem. And I just need to solve these two-dimensional dynamical systems. So you can just plug this in the computer, and then you can get the solution. And if you just, it's like simple algebra to show that the mean square error of AMP is going to be 1 minus Q of T. Yes. And the MMSE is going to be 1 minus Q star. Thank you. So remember, like the performance of AMP is going to be related to this variable, and you can check that this is just like 1 minus Q. And the MMSE, so the best mean square error you can achieve is the extremizer of the potential. So it's 1 minus Q star, where Q star is the extremizer of the potential, okay? So you get Q star, this is the MMSE, and then you have the MSE of AMP, which is 1 minus Q. And of course, the question we're interested is whether AMP and is optimal, in the sense that AMP is going to achieve the MMSE. Okay, so if you want an exercise, like just code these equations, put in the computer. That's what I always ask my first year grad students. The first thing for them is to code this kind of equation so that they get used to it. And if you plot the performance, the MSE, as a function of alpha, you get the following curve. So I have two colors. Let me do this one first. So that's alpha C. And then 0. Well, here you're going to have the okay. So that's the MSE of AMP. And that's the MSE of the optimal Bayesian posterior. So if you actually sample from the posterior and you compute the MSE achieved from the posterior, this is it. And that's what we call the alpha IT. So let's take a look at this image and let's parse them for a second. So what is this? So first, we are plotting the error that we achieve, and we are comparing two things. We are comparing the error achieved by AMP, and here I should mention it's AMP from random initialization. You don't have any information about the signal, and that's usually what you do in real life, right? You have no information about the solution of your problem, so you just initialize randomly. So the only information you have is the information about the prior, because we are Bayes optimal. So you sample from the prior, and you initialize at a sample from the prior, and then you run AMP. And we are comparing these against, you have information, like you have all computational capacity that you want in the world, and you burn it down to sample from the posterior, okay? And then you sample from the posterior and you compute at that sample complexity. Remember that alpha is n over d. So larger alpha is more data that you have. For that sample complexity, what is the performance of a sample from the posterior? Okay, what is the MSE achieved by, and this is the optimal thing you can do, right? Because that's the MMSE. The curve MMSE as a function of alpha. So essentially, when alpha is equals to 0, the MMSE and the MSE is equals to 1, which is the maximum error if you normalize things properly. So it's logical, right? You have no data, you cannot do anything, so you just have maximal error. As you start increasing your quantity of data, it reaches a point where you start having enough data that you can start correlating with the signal. And that's what we call the weak learning transition. So weak recovery, if you want. That's weak recovery. So this means that the overlap 1 over d, the overlap of your estimator with the signal converges to something which is larger than 0 when d is large. So below this threshold, this always converges to 0, while above this threshold, you start to obtain a small correlation with your signal. So you're partially recovering your signal. And that happens at the critical threshold. As you start increasing more data, there's going to be a point that your error starts improving and you get a big jump. And this jump is when it becomes information theoretically possible to fully reconstruct your signal. So that's what we call the full recovery information theoretically. Means that you can actually fully recover if you actually have the best estimator possible. You can obtain perfect correlation with your signal. However, what happens is that AMP is not able to achieve full recovery at that threshold. AMP is only able to achieve full recovery with more data. So at alpha AMP, while this is like the full recovery for AMP. Okay? So just to give you some values, so that's equals to 1. That's equals to 0.5 for this problem. And that's equals to 1.12. Okay? And this region that is in the middle, which is the region where you can information theoretically recover, but AMP is not achieving, is what we call a hard phase. And from the Celentano-Montanari results, we know that no other first-order method is able to recover the signal in this region, okay? And now I would like to give you a dual picture from that, which is the landscape picture. So this is plotting the MSE and the MMSE of the state evolution equation. So following this iterative equation. But let's look how this looks like in terms of this large deviation potential, just like we did for the Curry-Weiss model. So we need 6 plots. So I'm going to plot phi as a function of m in all of them. Okay, so I'm plotting this landscape. So m is a positive number because it's a. So I'm just computing like the positive side. So in this region where you cannot weakly recover, it's pretty simple, right? M equals to 0. Oh, sorry, not m. I should call it q. Because, yeah, I chose q. But m is equals to q due to the Nishimori properties. So in this region, you just have one minima, and this minima is 0, meaning that you cannot achieve any correlation with your signal. And you start increasing alpha, so this direction is increasing alpha. At some point in this threshold, what is going to happen is that this minima is going to become a local maximum, and another minimum forms down here, which is larger than 0, but it still is like, you know, it still is small. It's not 1. It's not perfect recovery. So that's the weak recovery threshold. And if you paid attention in the first lectures, you realize that this transition, when you have like a local minimum becoming a local maxima continuously, is a second-order phase transition, which means that you can compute this threshold exactly by just expanding the potential function and seeing the sign of the Hessian. Okay? I'm not going to do it, but you could do it to compute this 0.5 value. As you start increasing more your data, at some point, another minimum appears, but this minimum is not the global minimum. It's some local minimum. So the global minimum is still here, and there is a second minimum there. So you can only reach this minimum if you initialize your algorithm with side information, because this corresponds to Q, which is large. So if you initialize AMP at 0, you're stuck here, okay? But that's okay because that's still the global one. So that's still the information theoretically best one. So okay, AMP is actually achieving the information theoretically best one, which is somewhere around this region here. Now, as you increase more data, this minimum goes down, and eventually they cross up. So this is supposed to be like, the same level. And now you have this 2 minimum. And as you increase more the data, you increase more the signal to noise ratio, this eventually becomes the local one, and this is the global one. So this becomes the global one, and that becomes the local one. And that's exactly the point where you are in the hard phase, because if you run AMP from random initialization, you're gonna now be suboptimal, because you're gonna be the one which is closest to initialization, while the optimal one now is this other one. And the fact that you have an energy barrier here means that AMP is not gonna get there. AMP is gonna get stuck because AMP is extremizing T. So once it reaches this point, it stops. So this is the hard phase. And you can see that the hard phase is related to this metastability that we discussed in the curve-wise model, because it's exactly in the region where I have these 2 minima, and the minima which is closest to random initialization is the one that attracts local algorithms, and but is not global. And finally, as you start increasing more your signal to noise ratio, eventually your potential becomes convex again, and there is only one minimum. And this minimum is achieved by both AMP and by the Bayes optimal estimator, and that's you are in the easy phase. So that's called the hard phase. That's called the impossible phase because information theoretically you cannot recover. And that's called the easy phase. So easy, both AMP and information theoretically you can recover, can reconstruct. Hard, information theoretically you can recover, but AMP fails. And impossible, no one can recover the signal completely, okay? So this type of picture is behind many, many, many settings. I'm doing phase retrieval, but if you do like sparse PCA, if you do compressive sensing at very low sparsity, you do like Gaussian mixture clustering, you do many, many, many algorithms like that you can analyze with this framework are going to lead to exactly the same picture and exactly the same conjecture of hardness attributed to the fact that that you have metastability, and this is related to AMP suboptimality because AMP is actually minimizing this potential, and it is the optimal algorithm in first order methods. Okay. Okay, so I have 10 minutes. I just want to make a few remarks, but do you have any question about this picture? Yeah, sorry. I mean, it was at the same time, so yeah.
Yes, you explained that AMP cannot cross the barrier, but can anything else cross it? Or
yes. So, for example, okay. So let me make 2 comments. First, is that even AMP can get there if you initialize there, right? But you cannot initialize the signal in real life, right? Then the question is, are there algorithms that are agnostic to the signal and that can reach this minima? Yes, there are. So that was going to be one of my comments. So for this problem specifically, okay, polynomial time algorithms, I should say that. So for this problem, noiseless phase retrieval, there is one algorithm called LLL that essentially is a geometrical construction which has running time d to the dimension d to the power 6. So remember from Cynthia's lecture, AMP is d times n, right? Because you just need to multiply by a matrix. So yeah, that actually solves this problem and attains and achieves the information theoretical threshold exactly. So AMP is not optimal for this problem. No. The thing is that this landscape is the landscape of the Bayes optimal posterior, and for some magical reason, AMP is doing descent in this landscape. And because AMP is optimal in a class of algorithms, we believe that this picture is the correct picture of hardness for this class of problems. Now, other algorithms, let's say, in this problem, there is an algorithm which is famous, which is called the Wittger flow. A lot of people have studied that for phase retrieval. What Wittger flow does has nothing to do with that. It sees a completely different landscape, but the hope of the conjecture is that this is always the best. And whatever other polytime algorithm you have is gonna do worst. Now, as I said, with the caveat that this conjecture is not true, we know for this problem, like the noiseless phase retrieval, that there is a d to the 6 algorithm which is better. Now, you add noise. This algorithm breaks down. It doesn't work. So the kind of the conjecture that people like to believe is that AMP is, in a robust sense, the optimal polytime algorithm. So an algorithm which is not sensitive to adding noise and to very specific details of the problem. I'm going to make a comment about that soon, because there are cases in which you can prove equivalence between different concepts of hardness, between AMP hardness and other concepts of hardness from TCS.
I was going to ask, so I understand that in the hard case, you can't go over the barrier, but can you initialize somewhere else instead of starting at 0?
Yeah.
Like if I think of the Curie-Weiss model, instead of doing the random initialization, if I do all spins 1,
yeah,
and I'm starting from the right side,
yeah,
then if I come from right, then I go to the block.
Yeah, that's totally true. So that's actually a very good question, because okay, in reality, unless you have information about theta star, you cannot do that. But you can get some better initialization than random. For instance, doing something like a spectral method. So in the phase retrieval problem is a classic type of informed initialization. Is first you get your data, you do some spectral method, and then you run AMP. And then there are works on that. I think, Cynthia, you have work on that. Yeah. So also that there is work by Marco Mondelli, if I remember well, exactly analyzing AMP from this spectral initialization. But like, let's say morally, you want informed initialization that is not informed in the sense of knowing theta star, but something that is kind of agnostic of theta star. Something that you can just run with your data and then initialize AMP at that point. Spectral is the classical one, but there are other schemes that. Yeah. Questions? Oh yeah, that's a very good question, but I don't know how much time I have to go into that, but I can tell you one sentence, and then if you want, we can discuss more. Is that whenever you have a second order phase transition, like the one that we have here in weak recovery, you can linearize AMP. So you can get AMP and expand around this fixed point. And this gives you a spectral method. And this spectral method achieves the optimal weak recovery threshold for the problem. So it gives you, AMP in some sense, it gives you the optimal pre-processing function for the weak recovery spectrally. And yeah, so that's my comment. And this has been done for the phase retrieval. This has been done for other problems where you have this type of second order phase transition, which is typically associated with weak recovery. Now, we don't have spectral methods, for instance, for strong recovery. Like you cannot do a linearization of AMP around the first order phase transition because it's discontinuous. So you don't capture that by expanding. Okay, so let me just make one remark, and then I'm gonna wrap up. Which is about the relationship between AMP hardness and other notions of hardness. So AMP hardness is consistent to what is called SQ lower bounds. So if you know what this is, you know, otherwise I won't explain, but in this proportional regime, for different class of problems, for some class of problems that have been checked. I'm being, you know, intentionally vague here. So for some computational problems, you have this notion of complexity, which is called, like, you know, the SQ class of algorithms. These are algorithms that only access like some queries up to some noise, and then you can use these queries to run any time of any kind of algorithm that, you know, just uses these queries, and you can bound the error or the complexity of this class of algorithms. And you find that for some class of problems, like, you know, multi-index models, single index models, you can show that whenever it's hard for SQ, is hard for AMP, and vice versa. So so for single and multi-index models, there is work by Damian et al. In 24, 25, 24 for single index models, 25 for multi-index models. And that's related to also to a work by myself and some collaborators that we characterize the AMP hardness for this class of problems, and they showed that this is equivalent to SQ, and they actually SQ provides even like bounds beyond the proportional regime. So that's why I'm stating that equivalence is in the proportional regime, and then beyond the proportional regime is kind of an open question because we don't know how to do AMP beyond the proportional regime. Then B, so the AMP thresholds. So by thresholds, I mean these alphas, right? Alpha C, alpha IT, alpha AMP. They agree with what we call the low degree polynomial thresholds for, again, vaguely for some class of problem. When I say that, is like because, okay, this has been checked explicitly for some class of problems. That so the low degree polynomial method is a method of like also computing thresholds, like for which some class of algorithms fail or succeed. And you can it actually, differently from SQ lower bounds where you just get a lower bound, in low degree polynomial you can actually compute thresholds. Like, you know, this algorithm starts to work from that value of sample complexity. So these thresholds agree with the AMP for some problems that have been checked, and that's work by Alex Vine. And these ideas of low degree polynomials have been introduced by Hopkins. And final comments, which is something that I already said, but let me write. So AMP, which is like is not optimal poly D algorithm for some problems, for noiseless, for example, noiseless phase retrieval. So for noiseless phase retrievals, as I said, there is this LLL algorithm, which was studied by Elisabeth, I think João Bruno, and I don't remember the third author, but there's a third author in this paper in 2022, and they showed that this is a D to the 6 algorithm that actually achieves the IT threshold. So it's a polytime algorithm that achieves the IT threshold in the hard region. And as I said, when you add noise, things like this algorithm doesn't work. So it's still for noisy phase retrieval. Essentially, this picture doesn't change almost at all if you add epsilon noise. But the algorithm doesn't work. So we don't know whether AMP is optimal, for instance, for noisy phase retrieval among polytime algorithms. Only know for first order methods, which are linear methods. Okay, so let me wrap up because I see that I'm running out of time. So okay, so so first thing that I wanted to say is that here we just scratch the tip of the iceberg. Okay, so this type of my philosophy in these lectures is to introduce you to statistical physics, not as like, you know, something that you can study one problem, but like a mindset, right? It's a way of thinking about high dimensional probability. So we went on into this journey to think about like large deviation principle and inference problems and notions of hardness for polytime algorithms, but the same kind of ideas can be used to study other class of problems related to other fields of computer science, statistics, machine learning. So there are many interesting statistical problems you can study with AMP. You can construct, for instance, debias like statistical methods with AMP. You can construct methods to study like, you know, confidence intervals in statistics, uncertainty. You can study machine learning. So similar ideas to what I introduced here can be used to study, for instance, neural networks, SGD, GD. So there is a method called DMFT for writing down what would be the state evolution of gradient descent in terms of like summary statistics. So that's called dynamical mean field theory. There is some methods to study online gradient descent, stochastic gradient descent, due to a work of two physicists in the 90s. So David Saad and Sara Sola introduced this method to study one pass SGD for order parameters. So always the ideas are kind of similar. You start with a high dimensional problem, you write summary statistics for your problem, and you try to write your algorithm as as in the space of summary statistics. And in this low dimensional space, things are easier to analyze. So that's the philosophy of like, you know, the statistical physics mindset. So you can also study like problems in random matrix theory. So there is a whole world out there. And here, even in this context, we only scratch the surface because we only looked at replica symmetry. So what happens when you have non-convexity? What happens when you have replica symmetry breaking? So these are all like interesting things that you can still do. So I mean, my idea here is like, you know, to provoke you a little bit, so you are a little bit inspired by these methods. And then if this convince you and you like that, there's a whole journey ahead of you. It's like, you know, it's a lifetime. It's a whole research career, like to go deep into all these different methods and all the different type of problems that you can approach. But I hope that I conveyed a little bit the universality of these methods. So okay, so I'm gonna end here, and thank you for your attention in these lectures. It's been a very nice summer school.
I'd like to thank Bruno for